All right, hello everybody. Welcome to day 2 of 44Con. I hope you're all feeling at least as tired and rested as I am. Did everybody have a good night last night at the MWR party? All right. So today, starting off, we've got Phil Polstra. I just want to say a couple of things. Firstly, the sponsors have gone a long way towards subsidising the cost of the tickets. Please do see them today. Please make the effort to go around and talk to them all and grab some freebies if you've got them. I mean, entertaining and positive discourse. And the other thing is we could do with, we're going to do this next year. We want to know what we did right, what we did wrong, which speakers you liked, which speakers you didn't. We have survey forms and feedback forms. Please fill them in. So without further ado, here's Phil Polstra.
Good morning. So today I want to talk a little bit about USB flash drive forensics, some of the stuff we're going to talk about today. Very briefly, I want to talk about some of the basics of USB. Steve assured me everyone knows all this, so we're going to review. Talk about flash drives, a little bit about the technology in flash drives. Everyone uses them. Some of you have them hanging around your necks right now. Talk about forensic issues that are specific to flash drives. And then we're going to have the real fun. Talk about fun with microcontrollers. What can you do on the cheap with flash drives and microcontrollers? I think that Steve just likes to manhandle people. That's really what that's.
I do like to manhandle people.
Is that better? All right. It reminds me, you guys have probably more likely seen this show than people back in the U.S. The IT crowd. Have you tried what? Turn it on, turn it off, turn it back on again. I just recently discovered that show, lovely Netflix thing. And finally, I'll talk a little bit about a potential problem that you might run into trying to do some of this stuff I'm going to talk about, and an awesome solution that I came up with. So, all right, so basics of USB. We'll talk about the history of USB, a little bit about hardware and software. All right, so brief history. Back in the olden times, some of us are aware of these olden times, before 1996, we had non-universal serial bus. Everybody had their own specialized ports. Things were somewhat confusing. You had to configure serial ports to work with every single device. You had different kinds of cables possible, and you discover, oh no, that's not a null modem cable, that's a different kind of cable, and stuff didn't work. All right, so in 1996, they came out with USB 1, and it allowed you to connect things more easily from the user's perspective at speeds of 1.5 or 12 megabits per second. 2 years later, they said, we need to tweak that. USB 1.1 was born 2 years after that, USB 2. And they added another speed called high speed. And 8 years go by. In 2008, they released the USB 3.0 spec. And now we have potentially up to 5 gigabit per second speeds. All right, so hardware, you've all seen the hardware. The idea, it's a pretty simple 4-wire connection. You've got 2 data wires. You've got a power wire and a ground wire. And it's meant so that the cabling will prevent something improper, right? Which is good from a user perspective. It's bad from a developer perspective. If you have a device that's already got a couple of ports and it's not the port that you wanted, then you can search for a gender changer, or you can make your own, and things get a little complicated. But from the user perspective, pretty simple. Everything's hot pluggable, uses differential voltages instead of absolute voltages. That's a little bit less noise sensitive, and you can have up to 16-foot cables, right? So All this is good stuff. Software-wise, you want something that's automatic, that you don't have to worry about setting jumpers. And the way this works is a process called enumeration, where hosts and devices talk to each other and figure out what's going on, what they provide. The spec has a number of standard device classes, human interface devices, printers, audio, and mass storage, which is the subject of this talk. So, all right, enough about the basic stuff. USB flash drives. We'll talk about some of the things involved with flash drives. What does the hardware look like, software, what sort of file systems might one expect to find, and a little bit with how Windows deals with flash drives. All right. So here's a picture. I ripped it off of Wikipedia. All right, I'll just say that right up, of a typical flash drive. So what do you have? You have a connector. Right, so you have your USB-A connector here, and then you have a circuit board. The biggest thing on this circuit board is going to be a flash memory chip, hence the name flash drive. So typically you'll have a flash chip. This particular one pictured has a spot for a second flash chip that's not installed. And then you'll have a controller of some sort. Often you'll have an oscillator, usually 12 megahertz oscillator crystal. If you're lucky, and this is primarily on the older devices, you get a read-write switch, right? We'll talk about this a little bit more later, but today you typically don't find many flash drives shipping with us, which is kind of unfortunate, right? And if you're lucky, you get a nice little LED that blinks at you so that you know things are happening. And I have a couple of flash drives here, including some 4 gigabyte drives I got at my local Staples for a whopping $8. Unfortunately, they were only $8, but there's no flashing LED, so you don't know what's going on with this one. All right, software. Software typically is implemented in firmware inside a specialized controller chip. So there are a number of manufacturers that put out these chips. They're pretty generic. They read NAND flash memory. They talk USB, right? So what sorts of things must they do? They have to detect any kind of communication that's sent to this drive. They have to respond to standard requests such as, hey, tell me what you are. Please suspend yourself. Please stop suspending yourself. Things like that. They have to check for errors in transmission, manage power. Devices are allowed to request different levels of power, and they need to respond appropriately. Right? And they exchange data, of course. All right. File systems. What kind of file system can you put on this flash drive? Well, the flash drive presents itself to your computer as a block device. It essentially tries to emulate a hard drive, and it says, I am a hard drive, typically a hard drive that has a bunch of 512 byte sectors on it. Right? And you can do whatever you want. Any kind of file system you can put on that. Almost every flash drive you ever buy, though, is probably pre-formatted with FAT or FAT32, more likely FAT32. But sometimes you will find a drive that's formatted with NTFS. Right? Now, there are a number of flash-specific file systems. You get the true flash file system, the extreme flash file system, the journaling flash file system. One of my favorites is YAFS, yet another flash file system. All right. And of course, you can also put your favorite Unix or Linux file system. You can put X4, X5, whatever you want on there. Riser file system, whichever you prefer. So it presents itself as a block device, so it's pretty flexible on how you can connect it. Right? So let's talk just a little bit about Windows. How does Windows respond to flash drives? So we'll talk about what happens when you connect a drive. How do you block write operations if you don't have one of those lovely switches? And how do you figure out who was there? You know, what has been going on USB related on your computer? Right? All right, so here's what happens when you connect a drive. You know, it all seems very simple, right? You plug it in and you get the little noise, right? So you plug it in, you get the little noise. Must be easy, right? Well, if you dig into this, by the way, you get involved in the whole USB, what's going on, and you start building devices, it gets a little addictive. And I think the reason for that is that there's 12 steps. You know, I don't know if you guys have 12-step programs here for addicts, but I'm guessing you do. So here are the 12 things that happen. You connect your device. The hub, which is the piece of hardware on your PC normally, there's two sides of the USB. There's the slave or device, and then there's the host side. So the PC is normally on the host side of this. It detects that a device has been connected, and the hardware, the hub, informs the host, usually the PC, hey, somebody connected something. So then the hub determines what kind of capabilities this device has. And how does it do that? It sends a bunch of signals, and you know, you can read the spec if you're really interested, but sends a bunch of signals, and it determines how fast can this device operate. Can it operate at 1.5 megabits per second, or can it operate at 12? And it determines that based on where these pull-up resistors are installed on the device, right? So once it's determined that, then the hub says, thank you for telling me about yourself, now reset. So it resets the device, and then it says, hey, you said you could do 12 megabits per second, can you do 480? And the mechanism for that is a little different. They don't just use pull-up resistors, in part because of backward compatibility. Right? You want your device to be backward compatible to a USB 1 hub. So what it does is it sends a bunch of signals called chirps, and based on the responses, the device, you know, if the device responds, essentially it's saying, oh yeah, I know what you're saying, I know how to do high speed. Right? Once that's done, it establishes a signal path. The signal path is a set of endpoints, and these endpoints are used to communicate between the device and the host. All right. So now we've got communications, we've established a speed, and all that's left to be done is to figure out what it is that this device actually does. So it asks for a descriptor, and descriptors, there's a whole set of descriptors available from the device that tells it what is the maximum size packet that you'll take. Once it's done that, it assigns it an address. It says you'll be device number 1, right? Most likely if you're the first device. And then it's going to enumerate through their capabilities. Once it's figured out, oh, you're a human interface device, or you're a mass storage device, Windows is going to load an appropriate INF file, a device driver, right? So if you have a standard flash drive, if I have, you know, this is a little SanDisk drive, if I have Patriot memory, whoever, if I have somebody else's drive, Windows doesn't have to have a custom driver for everybody's drive. They all use the standard interface drive. Now, some drives might use a custom driver, in particular if you get encrypted drives. I didn't bring it with me, but I have a flash drive that takes fingerprint scans. You may have seen things like this. Typically what they do is they have their own custom driver and only unlocks with the fingerprint. But, which is really annoying if you like to run Linux, because they don't provide a Linux driver for that, but it is an option. And finally, a device can have more than one configuration available. Most of them don't, especially flash drives. Typically they have one configuration, and then the device says, this is the configuration we're going to use. All right. Very simple, right? Makes the little noise, you plug it in. That's all that's going on behind the scenes. All right, as I said before, often you want to block write operations. And if you're lucky, you have a little switch on your drive. You don't see that so much anymore, unfortunately. There is a workaround that kind of works. Right? If I want to block write access to every USB device, right, that's the downside. I can't say, well, you can't write to that one, you can only write to this one. Now, yes, I could write software that detects the different devices, and I could go about it that way. But if I want to do this very easily, I can go into the registry, and I can find this key under local machine, system, current control set, control storage device policies, write protect, and all I have to do is create that key if it doesn't exist and put a 1 in there. Now I can't write to any USB device. Right? Why would I want to do that? Maybe I work in a sensitive organization and I don't want all of my employees stealing information by plugging in their flash drives and taking them home. Right? By the way, my preferred solution for that is called hot glue. Hot glue and then USB ports does wonders. You'll see a little later, I have this love for hot glue. It comes in handy for many things. But other options, you can buy commercial write blockers. The cheapest commercial write blocker I was able to find cost around 800 US. That's the cheapest one. I'm going to show you something that you can build for about 25 euros. 25 euros, what, 500 euros? It's a hard choice to make there, but and we'll discuss that a bit later. By the way, other reasons you might want a write blocker, not just for forensics. If you're like me, you have some flash drives that have all of your great tools and your toys, right? Maybe Katana, I'm sure several of you have heard of Katana. Great tool. What happens if I'm walking around the university and I want to get something off one of my flash drives, I plug it in, and I forget what's on the drive? What happens to me? All of a sudden a little message pops up. Oh, the university's antivirus has detected horrible malicious software, my tools, on this flash drive, and what is it going to do? I am helpfully deleting them for you. So, you know, then there are times like that where you wish you had the right protect switch or something like that. So we'll talk about that. All right, Windows. If you're doing Windows forensics, Windows is great at storing all kinds of information in the registry. Right? You guys are probably all aware of this. Your average user is completely oblivious. And even the moderately sophisticated user that thinks to, you know, delete their files a little better probably doesn't even think about going into the registry because it's a scary place, right? So nobody wants to go there. So the registry stores every single USB device that was ever connected and all kinds of information about it. And you might think, why did they do that? Did they do that for forensic investigators? Well, maybe not. They probably do that so that when I plug in a device the second time, it's a little faster. Because it says, hey, I know that device. I know what to do. Last year, I taught a cyber forensics class at the university, and I gave this assignment, and I thought this is going to keep my students busy for a couple hours. I said, all right, I want you to go in this computer lab here, and I want you to tell me about every flash drive that's ever been plugged in to these devices. 5 minutes after I gave this assignment, I thought, okay, I got a couple hours to just kind of kick back and relax. One of the students is sitting there, and he goes, all right, everybody, I just Googled it. You go to get this thing called USB Dev View, and boom, you can do it. All right, here's a screenshot. I'll also show you a live, here we go. There's a live instance of this tool, USB Dev View. Nice little tool, and it'll show you, here's all the devices, different types. I've got it sorted by type, so you can see all the human interface devices I've connected, mass storage devices. Is it currently connected? What's the drive letter assigned to it? Last time it was connected, serial numbers, create date, vendor ID, product ID, firmware version, what kind of USB device was it? All these lovely things it'll tell me. It goes on and on and on and on. All right. So something to keep in mind, next time, in the movies, what happens, right? In the movies, somebody connects their flash drive and they download the secret information and then they get busted later. Well, how did they get busted later? Well, there's all kinds of information in there. So the moral of this story is just don't run Windows. But all right, so I was somewhat, but only slightly disappointed by that, though. My students were thinking, oh, Phil's going to be really mad because, we found this tool to do this thing in 5 minutes. And 5 minutes later, I'm getting all these reports from my students. They went home early that day. Right? It was a 1-month class. And I thought, well, that's great because they're working smart, not working hard. So I actually was kind of pleased and surprised that they managed to do that. All right. So let's talk a little bit about forensics. When we talk about forensics, others such as Gareth yesterday have told us what forensics is, investigating stuff, usually as part of a criminal investigation, not always though, but when we look at flash drives, we can treat them either as memory or as storage media. So when we look at a flash drive as memory, typically flash drives use flash memory. Well, there are different kinds of flash memory. There's NOR flash memory and there's NAND flash memory. Sounds kind of like or and, all right? And it refers to the way that the flash memory is accessed, all right? NAND flash memory by far is what you're going to see in flash drives because of speed, but primarily because of size. All right, NAND flash strips are much smaller. What are some of the downsides of flash memory? Right? You can only write so many times to flash memory, typically about 10,000 times. After that, the memory degrades, right? And you have issues. Other things, most of these chips aren't even close to high speed, 480 megabits per second. In particular, if you're writing to them, they're nowhere close. A little bit later, when I show you some fun devices, you'll see that they're limited not by the device, but they're limited by the flash drives. The flash drives can only write so fast. So what really kills me, you can get a flash drive, and some of them will even advertise supports high speed. Okay, it does support it, but that doesn't mean you're going to read off of that chip at high speed rates. It also means you're certainly not going to write anywhere close to those rates. You're not even going to write at 12 megabits per second. Right? But it's good advertising, I suppose. Other downsides of NAND flash memory chips, you can only write chunks. You can't write one little byte. Right? So what happens if I want to change one little byte? I read out a chunk, I change the one little byte, and I put back the chunk. Right? In some cases, the chunk sizes for the read and the write aren't the same either. A lot of this is handled by the controller. Yeah, it's really crazy, I know. MacGyver's laughing at me here. But, reading and writing in blocks, as I said before, typically those blocks are 512 bytes. Some of the newer drives do have 2K byte sector sizes. or maybe 4K. I don't think I've ever actually seen one. I just heard that they exist. You know, and I've had some largish, like 32 gig flash drives, and they still have 512 byte blocks, which is horribly inefficient, especially when you're running FAT or FAT32. But all right. Other things you can do, if you have a flash device and it's been damaged, you know, yesterday Gareth showed us some really damaged hard drives. If you have a highly damaged flash device, you can normally somewhat easily unsolder that memory chip. As long as the memory chip isn't bad, get another flash device and solder it on there and read it. You don't have those issues that you would have with a hard drive where, oh, I'm sorry, you know, like the Sony hacker. Oh, that printed circuit board just disappeared. I'm sorry. Right. So if you're really lucky, you might have a JTAG port. For those of you who aren't familiar, JTAG is a standard for testing. It allows you to connect to a device and do some testing on it. Other things that you should be aware of. When you buy hard drives, they cheat a little bit, right? You buy the gigabyte or the terabyte drive. It doesn't really have a terabyte. It has, you know, a trillion bytes, not 1,024 times 1,024, et cetera, right? So you can have slight differences. If you buy a flash drive, you should be aware there can be slight differences as well, because some of those controller chips I talked about a little while ago, some of them have their own RAM and their own storage, and some of them steal some of your flash memory. Right? So if you have two 4 gig flash drives from different manufacturers, they might have slightly different amounts of storage, which might be bad if, say, you were trying to make a forensic copy of the larger one to the smaller one. All right, so something to keep in mind. All right, as a storage media, it just emulates a hard drive, typically with a SCSI interface. And as I said, 512 bytes is the typical sector size. Often they'll use the SCSI command set. And typically, a flash drive is formatted as just one big partition, right? Or logical unit. The flash drives can support multiple logical units. However, they're treated differently in different OSs. In theory, Windows can read other than the first logical unit. I have never seen that happen, though. Maybe I haven't used the right version of Windows, but typically I can hide information on higher logical units. Right, so if I have information I don't want someone to just naively get, if I plug it in my flash drive, I just put it on a higher logical unit. Now, if I'm really paranoid, well, first of all, of course I'm running Linux, right? If I'm paranoid, I'm not running Windows, but you can use an encrypted file system and put that on a higher order logical unit on your flash drive. Just a little tip for stuff that you don't want disappearing or people looking at. So, all right. Other things you should check, the device will report its size, and then it has its real size, right? There have been a batch of some really cheap drives coming out of China. This was a few years ago. They would advertise themselves as perhaps a 4 gig drive, and they were really a 1 gig drive. And I guess they figured that it'll take a while for someone to notice. You know, all of a sudden you get over a gigabyte and you get all these errors. Why can't it write to anything? Because it's not there. It was a lie, all right? Other things you should be aware of, you know, on the hard drive game, you know, 1,000 is 1,000, not 1,024. Well, you might think, well, since we're dealing with memory chips, when it comes to flash drives, we don't have to worry about that. Well, that's not quite true because of two things. I already mentioned that some controller chips use part of that memory for themselves. And the other thing is you need to realize there's error correcting bytes. There's about 16 bytes for a 512 byte block. So it really takes 528 bytes to store 512 bytes. So you lose a little bit. Right? Okay, so let's get to the real fun. Let's have a little fun with microcontrollers. I'll talk a little bit about the chip choice that I made for making some devices. How do we talk to flash drives? How can we make very small? I want to claim I have the world's smallest forensic duplicator. You can challenge me on that later. And I have a slightly larger but more user-friendly version, and then talk a little bit about using a microcontroller to block write operations. All right, chip choice. I chose a Vinculum 2 chip from FTDI. You guys ever heard of this company? They're a little north of here, I think Glasgow, I think, is where they're at. But they do a lot of USB stuff. Anyone ever heard of Arduino? Right. The little chips that make your Arduino talk to your PC. Guess who makes those chips? FTDI. All right. They seem to be the USB people. They do. If they do it, it probably has something to do with USB. Well, I guess they got tired of just building those chips, and they decided, hey, everyone's got their own microcontroller. Let's make one. So they introduced this series. This is the second version of the series. And what does it feature? All right. You've got two full-speed USB 2.0 interfaces, and you can configure them as either a host or a slave. 256K of flash memory, that's respectable. 16K of RAM. Sounds low if you don't do microcontrollers, otherwise you're like, oh, it's pretty good. And they have all the normal microcontroller kind of stuff. Right. Also comes with an easy to use IDE, some simultaneous access you can do between devices. They have different development modules available. Unfortunately, they only make surface mount chips. I don't know how many of you like to build electronics and like to solder. I don't know too many people that like to solder with surface mount chips. Right? It's a bit of a hassle. In particular, you have to make a board, right? You can't just, oh, I've got this chip, let me build something with it. You have to make a board and, do all the etching, and it can be a little bit involved. So fortunately, they do produce some development boards, which are essentially just their chip with a big pinout, It's like, oh, I can plug this on a breadboard now. It's a little easier to deal with. And those devices, their development boards are cheap enough that you might just, instead of just breadboarding it, you might just plug it into an actual device, which is what you'll see here in a bit. All right. So they have, as I said, surface mount packages. Here's a block diagram. I don't know how well you can see this, but they have a little embedded CPU, some flash memory, the little bits that talk USB, and then kind of standard microcontroller stuff, general purpose I/O, SPI. If you don't know what SPI is, it's a real common thing that's used to talk between microcontrollers and devices and things like that. But you can ask me more about that later. Their IDE isn't bad. Looks kind of like this. This is stolen from their brochures. I'll show you the actual ID here in a bit. And, people ask me, well, what do you think of this IDE? And it's like, well, it's not Eclipse, but it's nice. It's very functional. I've had worse. And yes, it's not Eclipse, but I'm not building large operating systems or anything like that either that fit in my 256K of flash memory, right? So I just pulled up a project here. This is actually, well, what's going on there? This is a duplicator actually, but you know, it's pretty basic, kind of the stuff you would expect, where you can edit your code and get messages and set breakpoints and set up watches and et cetera, all right? Another nice thing that they have is they have general purpose I/O on the chips, and you can set that up, and they have a nice GUI like so that you can use for that. And here's one of their development packages, right? This is a 64-pin version. They have 3 versions of their chips. They all have the same functionality, it's just different levels of I/O. 32-pin, 48-pin, 64-pin. All right, so this is a blow-up. No, this is not actual size, all right? It'd be hard to fit in your pocket. Of the 64-pin version, you'll see an actual one here. Well, this is actual size, like that. And they also make smaller, such as 32, and you'll see that shortly. Here's a schematic for that development board. Pretty much, it's all going on here. They have pinouts for the chip, and then there's a couple connectors to do USB stuff. All right. So my first project, I said, you know, why don't I make a nice simple duplicator, just something that you can make a forensic copy with, a sector by sector copy. You know, you insert your drive to copy, you insert the target drive. Ideally the same model. We talked about the fact that it should be at least the same size. You might want to check that. Hopefully uses the same block size, not a problem. Everybody seems to be using 512, and then do a sector by sector copy. Right? Well, because of the write limitations on flash drives, and this does vary a little bit depending on how cheap they are, it takes about 11 minutes to do a gigabyte. All right, so if you have a 4 gig drive, 45 minutes or so, maybe an hour, and it'll be done. Right? And it's kind of a pay now or pay later. Either you pay now by making a duplicate as a flash drive, or you pay later by doing an image, which might be faster, but then working with the image is going to be slower. Or maybe you actually just want to make a copy. Maybe you want to make a copy of your Katana drive, you know, and you want to do a sector by sector copy to make sure that the new one boots when you're done. All right. So how do we talk to a flash drive? Very quickly, it uses what we call bulk-only mass storage, or sometimes called BBB, because there are different kinds of transfers that are allowed. A lot of devices use the control endpoints to control their transfers. Bulk-only mass storage devices do not. They use the control endpoints to enumerate, and then everything is done with bulk endpoints. Right? So they send out stuff. They have 3 phases. All right. There's a command block wrapper that's sent. Sounds like it must wrap a command block. All right. Possibly some data transport, and then there's a command status wrapper that comes back. All right. And pretty much all these drives use a reduced SCSI set. Right? And everything, as I said, is on bulk endpoints. Here is a little C code for a command block wrapper. What does it look like? We start out with a signature. There's a tag. The tag is used to associate this command block wrapper with the command status wrapper that comes at the end, so that I know which one I'm talking about. How much data am I going to send? Any flags? Is it in or out? Which logical unit is it? What's the length? The length is the length of my command block. Right? I have 16 bytes, and I'm going to use between 6 and 16. All right? The smallest command uses 6 of those. So the command block, as I said, is 6 to 16 bytes. The first byte is the command. So for example, the command to format your drive which is something you might want to do because it's quick and autonomous. You just do, boom, format, and it's a lot quicker than writing zeros to the drive. All right. So, the operation code for that one is 4. You can tell it which LUN you want. Here things get a little weird because they don't have everything on byte boundaries, so you have 3 bits for the logical unit number, extra parameters, et cetera, et cetera, et cetera, right? Here's an example of the read command block. There's different versions of this. This is called the read 10. And it's going to have an opcode of 28 hex, and here are the different parameters. I won't go into that because it's a little bit limited on time, but okay. Here are some common SCSI commands that you'll find useful. Most every device will implement these. Some of them I have listed as required. That's required by the SCSI spec. So you'll notice format units required inquiry basically says tell me about your device, and mode select says this is what I want to use to talk to you. And then there are different versions of read, some of which are required. And read capacity says how big are you. Read format capacities is how much real space do you have after you've been formatted, all right? And of course, we have to be able to write, and there are commands for things like synchronize cache. If you've been caching and I want to unplug my device, please sync it so that I don't have any data corruption or data loss. All right, once this has been sent, you have a command status wrapper that comes back. And it's much simpler. You have the signature, the tag that associates it with the appropriate command block, and then you can get a residue that tells you what's the difference between how much you asked for and what you got, right? And then most importantly, you have the status. 3 statuses are possible. 0 means everything's good. 1 means everything's not good. And 2 means a phase error. And you might think, what does that mean? I don't have time to go into it right now, but if you're interested, we can talk about it later. They use phasing to send commands and send information on the USB. So they'll use data 0, data 1, and they go back and forth, and there are rules, and going back and forth as to where you're toggled, either on 0 or 1. And if you get out of phase, then you send a phase error, which means, okay, I'm not sure where we are, let's go back to 0. All right. The reason that it's just simply 1, it's historical SCSI drives in your machine. You just want to check for 0, oh, it's 1, then you inquire to see what the error was. It's a lot faster than saying, is it 0, is it this, is it that? Sometimes you just want to know if it worked or not. All right, so. All right, just a little bit of code. Here's code that will connect to a flash drive, a bulk storage device, using this chipset. Very briefly, you start off, you create a handle to a bulk device, you set up a bunch of variables, you connect to it, you say, hey, I want to talk to a mass storage device, and one that speaks SCSI, please. They all do. And the protocol will be this bulk-only mass storage protocol we've been talking about. And I want to find a device handle by the class, which is what I've specified here. I make an IO control call. And hopefully at the end of this, I have a handle to a device. So now that I have a handle to the device, I open it. I attach to it. That might seem a little weird. Why do I open and then attach? But that's just the way it is. So another IO control. The cursors seem to disappear in this room. I think it's a Bermuda triangle or something. I know it's not just me because other speakers have. Does anyone see the cursor? The hidden cursor? There it is. All right. All right, and so we attach, and once we've attached, we do some stuff, and then we detach. Right? How do we read and write sectors? There's stuff provided in the library. Again, once I have a handle to the device, I tell it which sector I want, and I attach, and I was waiting for Steve to pick up that gun. All right, apparently I'm not that late yet. So, off we go, and we can read in sectors. Now, one thing you should be aware of if you're doing this kind of stuff, you can read in an individual sector. Many of these devices like to read and write in clusters. So if you read in one sector at a time, but they really have clusters that they're working with, what happens is if I read in sector 0, it's going to read in the first cluster. And then when I read in sector 1, it's going to read that cluster in again, and again, and again, and again. All right, so it ends up being pretty slow. So you want to try not to do that. All right, now here's the device realized. And I have to apologize. I know that in this country you have an aversion to the letter Z or Z as you call it here. So I apologize if my use of the letter Z offends you. I would write an apology, but if I apologized in writing, then I might use another Z, and then, the cycle continues. So, all right. So in order to improve performance over the simple-minded way of doing this, I implemented a double buffered, multi-threaded algorithm for this. Again, performance is still limited by write speeds of the device. Some future enhancements that I intend for this to actually use that format unit and then detect stuff that's all zeros, because often most of it's empty. Why should I write zeros all the time? It doesn't make sense in this context. Hard drives, it makes more sense. And it might speed things up a little bit. For this particular device, I use the smallest board that Winkler makes, or FTDI makes. And I actually took one of their development boards and hacked it a little bit and soldered directly to the board. Right? And it's got a nice debug port. Here is, you can see the scale. Here's blown up, here's actual size. Notice I have a convenient carrying tin from Altoids gum, all right? So, here's the actual, oops. See, it's so small, I dropped it. Here's the actual device based on a 32-pin development module. I just unsoldered the pins, the header pins on this, and soldered my LEDs and my power connector directly to it. Why did I unsolder the pins? Mostly because they poked me in my pocket before I got the stylish carrying tin. All right, so how would you power such a device? Well, it's a USB device, isn't it? So naturally, one would have to get a USB power cable to power your USB device. Right? Makes sense. By the way, this cable I reclaimed off my broken Wii recharger. It went bad, and I thought, yeah, that's a nice cable. I could do something with that. So, part of why you might want to do any of this is to avoid having to use a computer, lugging a computer around to do things. Nowadays, since I got my Android tablet, the only thing I use my computer for is programming things like this. But you might not have that. You might be traveling. So you might need some power. So you get your other Altoid gum tin, the one that has a little bit of circuitry and a couple rechargeable AA batteries that'll boost your 3 volts up to 5 volts. And you just plug it in and you got power, right? And this guy, he speaks Blinky. He doesn't speak English. He's not American English or British English. He speaks Blinky. And green Blinky means, please insert your original. So I can grab a drive over here. Let's see what happens. He went from green Blinky to yellow Blinky. What do you think yellow blinky means? Any blinky scholars in here? Blinky. Yellow blinky means please insert your duplicate or your target device. All right, so now he's on solid yellow, and if you watch, you'll see blinking lights here, all right, indicating access, and over time, you will see these lights sequencing. All right, that's my, see, it just went to the next LED. Every couple thousand sectors, it'll do that, all right? That's its way of saying, I'm not dead, all right? And then when it's done, red, I know it's probably a bad choice, but red on means I'm done now, right? So, well, he's not staying there, yeah, but, so that's my world's smallest. Now, you might object and you might say, well, that's nice, Phil, but maybe I could use a little more space. And so maybe I want to use a more user-friendly interface. I want to use the same code because I'm lazy. Good programmers are always lazy. So let me augment the blinking lights with some English. Also like to power it maybe with a 9-volt battery, make it a little simpler. All right, so I was originally hoping to fit this in an Altoid tin. It was just a little too big, even though I did shave a little off the circuit boards to make it fit. But I did get it to fit in a puzzle tin. All right. And so you might say, why the puzzle tin? Why this puzzle tin? Because if I took the Cars tin away from my son, he would scream. So the Mickey Mouse and Donald Duck tin, not so much. All right. So Steve's all cocked and ready there. So this is the slightly more user-friendly version. All right, so what I've done here is I actually took a 64-pin development device. Did I need that? No, but I had one laying around. So, and an LCD screen, and those both nicely fit on top of a little perf board that I had laying around. And onto that, I attached a switch, 9-volt battery, a 5-volt power regulator, and a pot to adjust the lighting on the LCD. So, right, that, oh, I got it upside down. So there you have the slightly more user-friendly version. And now it's saying, what does it say?
Insert original.
Insert original. All right. By the way, in terms of your battery life, what do you think sucks a lot of power on this? Backlight. Backlight on the LCD. Incidentally, I lost all this in my luggage. I checked because I didn't want to walk through the airport with all this homemade stuff. And I thought that the fact that I beefed up the power lines coming to the battery is a big no-no. You know, we did start 10 minutes late now, Steve.
Yes, this is true. However, one shot to the head for every minute in the world.
All right. So.
Go if you want. I don't mind. I just get to shoot.
All right. Well, here's some more pictures. You know, I'll be around if you want to see that later. One last device that I wanted to talk about real quickly is the right blocker. This is a device that I've had a couple of issues with this device. FTDI has come out with their Arduino clone, originally called the Vincolo and now called the Vinco. They can't decide what to call it. Looks about like this, and of course it fits in a puzzle tin too. And this is eventually going to be a USB write blocker. I say eventually because some of the issues I ran into, catch me later if you want to hear more about that. I didn't quite get this to where I wanted it before today, but all right, some future directions, using something like this to make an Android open accessories device. I did test their demos of that and it works well. And possibly some high-speed devices. All right. Last thing I want to see before Steve reloads is one potential problem with this is that some might object. Sometimes if you end up in court, you might want to have a certified device, and the solution to that is a new organization that I'm in the process of starting for. It's called the Open Source Cyber Forensics Association, and what is it? It's about giving people a place to collect hardware and software specs for security and forensic stuff, kind of like the Arduino of the InfoSec space is the way I like to think of it. Like what Arduino is to microcontrollers, OSCFA hopes to be for InfoSec and security. So you can ask me more about that later. Here's some books that I referenced, and I'd ask for questions, but Steve will shoot me again. So I guess I'm done. I'll be around if you have questions.
If I could make a quick suggestion, completely that on the fly, would you be willing to go to the workshops table?
I would certainly be willing to do that.
People more depth, so we are running over.
Yeah.